Hello, welcome all of you again to this NPTEL online certification course on fundamentals of composites and cellular materials, and I am Tapas Laha. So, for last few classes we are talking about fibers. So, initially we talked about the basic synthesis routes of fibers, then we started talking about commercial fibers such as glass fiber, carbon fiber. We have talked about these fibers. We also have talked about organic fibers. So, in today's class the plan is to talk about SiC fiber and whiskers. As I was mentioning, in last class we have discussed about organic fibers, their synthesis, properties and application, and then we moved to ceramic fibers. We discussed the fundamentals and basic synthesis techniques of ceramic fibers. We also talked about ceramic fibers in terms of alumina and their synthesis and properties and application, and we want to move on this ceramic fibers itself. So, today I plan to discuss about SiC fiber and their whiskers and what are the basic synthesis techniques and applications and properties as well. So, let us concentrate first on how we could synthesize SiC fiber. So, before I talk about the synthesis of SiC fiber, basically as you can see here, SiC fibers diameter range from 5 to 150 micrometer, and primarily it is composed of SiC molecules. Now, as it is a ceramic fiber, it obviously has very high strength, high stiffness, the density is quite low, and because of its ceramic nature, it is highly resistant to chemical attack, and also it is withstanding at very high temperature, and it has low thermal expansion. And as you can see here in this particular picture, because of its high temperature property, SiC fibers are used in this new generation G jetline engines as fibers, SiC fibers. Now, coming to the synthesis of SiC fiber is synthesized by chemical vapor deposition technique. I mean, that is one of the route by which SiC fiber could be synthesized. Now, if you remember, when we talked about boron fiber is also synthesized by this chemical vapor deposition. That means you need a substrate. So, you will be having there will be a substrate. On that substrate, SiC will be deposited and in the form of a fiber. So, again, just like boron fiber, SiC fibers are also composite in composite nature. That means, if you look at the cross section of SiC fiber, there will be a core, and then around the core SiC will be deposited like this. Okay. This core is made of tungsten, and on tungsten SiC will be deposited by the process of chemical vapor deposition. So, you can see the setup has been shown in this particular picture. So, this is the CVD chamber or chemical vapor deposition chamber, and then you can see there is a tungsten wire going through the axis of this chamber. So, basically it is a moving tungsten wire, and the diameter is around 13 micrometer, and the plan is to deposit SiC on this tungsten wire. So, again this tungsten wire has to be deposited at a particular temperature, and what is the reaction takes place in this case? So, obviously you need a precursor gas which is CH3 SiCl3, and this is called methyl trichlorosilane 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 , 2 methyl trichlorosilane, and at higher temperature CH3SiCl3, so around temperature in between 1100 degrees Celsius to 1300 degrees Celsius, CH3SiCl3 gets dissociated and it gives SiC. So, it is this precursor is gaseous, and then you have after the dissociation SiC as solid and then HCl as vapor. So, this is the basic reaction by which CH3SiCl3 or methyl trichlorosilane gets dissociated and it forms SiC solid, and this solid SiC gets deposited on the fiber. Okay. Now, what extra thing is required here? A catalyst, hydrogen is required to control this reaction. So, let us just look in the setup once more. So, this is the tungsten wire, and then obviously there will be an inlet. Through the inlet, this hydrogen, a mixture of hydrogen and CH3SiCl3 will be incorporated, and the ratio is in the range of 70 to 30. And then this tungsten wire is heated by applying a DC bias voltage, and then at that particular temperature the reaction takes place as I mentioned earlier, and SiC gets deposited on the surface of this tungsten wire and the exhaust gases goes out. As you can see here that only 5% of the original gas gets used, 95% comes out, and obviously HCl vapor also comes out, and this 95% original gas has to be again recycled back to the inlet. And ultimately, as you can see, in around 20 seconds 100 micrometer fiber could be synthesized by this method. Okay. Now, I was mentioning about, so this is the reaction, as you can see here, CH3SiCl3 gets dissociated and it gives SiC solid and HCl as vapor. Now, I was mentioning about the hydrogen partial pressure as the catalyst, and I was also mentioning earlier that the role of hydrogen is extremely important. You know, it has to be optimum. That means if hydrogen is more or less, you do not get stoichiometric SiC. So, if the hydrogen partial pressure is lower than the required, then more free carbon, in this reaction, the reaction gets controlled by the hydrogen partial pressure. So, if you have less hydrogen, then more free carbon comes into SiC, and if there is more hydrogen, then there will be more free silicon. So, it has to be very optimally controlled that you maintain a particular hydrogen partial pressure, so that the stoichiometry of SiC gets maintained. Now, why this stoichiometry is important? Because based on that, the property, especially the elastic modulus and strength, varies because of the change in stoichiometry of SiC. So, we will talk more about this factor, that the optima what is the requirement of hydrogen partial pressure. We will discuss more in details in few minutes. But let us move on now. Let us look at the cross section of this SiC fiber. So, you can clearly see in these three pictures, basically this is the cross section of SiC fiber, where tungsten core is clearly observed, and then around this tungsten core SiC gets deposited. So, it is a fractured surface and it shows brittle failure. Also, one more thing is very important here, that on top of the SiC surface there is a thin carbon layer is deposited, and that is basically to protect SiC from any kind of interfacial reaction when it is used in composite material. An example has been shown here where copper matrix has been reinforced with SiC fibers, and you can clearly see here this is the fiber, and then here is the copper matrix which shows nice ductile failure. Okay. So, now as I was talking earlier that we will discuss more on the effect of hydrogen, let us talk about a particular example where if we vary the hydrogen concentration or hydrogen partial pressure, how the morphology and the phase changes and how the property gets changed because of that. Let us discuss that in this particular example. So, here as you can see here, this is a SiC fiber. Tungsten has been deposited on this SiC fiber, and then what is clearly observed, can be clearly observed, is that there are two layers, two different layers. So, the whole thing is SiC, but then the morphological difference can be seen in terms of the two layers. For example, here you do not really see any kind of grains as such. At higher magnification you could be able to see, and then there is a clear interface, okay, and then after that the layer 2 starts, where SiC are more, the grains are elongated radially, as you can see. Okay. A schematic has been shown here, is that this is the tungsten core. Basically this schematic is based on this particular microstructure. So, you can see here that this is there is a tungsten core. Around the tungsten core you have around 44 micrometer of SiC getting deposited. In that there is layer 1 which is around 22 micrometer, and then layer 2 is around 20 micrometer, and on top of that layer 2 there is a carbon coating. Okay. And as I mentioned earlier, a clear interface can be observed, right. Now, so whatever I just mentioned, those things has been written here. So, now let us look closely in this layer, on this layer, that what exactly are there, or how is the morphology. So, now this one is the SiC1 layer. What can be observed here very clearly, that the grains are very fine. That is the first observation you can see. Also, there is no preferred orientation or preferred growth of the SiC grains in this particular layer. And then once you move from SiC1 layer to SiC2 layer, again you can clearly see that there is an interface, clear interface, distinct interface, and beyond that, if you look at the SiC2 layers, then you can see nice elongated grains, and this elongation or the orientation of growth is preferred radially outward. That means from the tungsten core towards the outer surface, and obviously then at the outmost layer there is a carbon coating. So, as I was mentioning earlier, that SiC1 layer contains very small grains with random orientation, and there is an obvious interface between SiC1 and SiC2, and the SiC2 layer, if you look at the SiC2 layer, then you can see clearly those elongated columnar grains. As you can see here, these elongated columnar grains parallel to the fiber radius, and the SiC grain becomes larger and the direction becomes ordered gradually with increasing distance from tungsten core. Again, it is a very important observation here. As you can see here, this is more clear here. So, as you move from the core towards the outward direction, you can see here the grain size increases, and the elongated grains also becomes more elongated as you go outward radially. So, now we need to understand why this thing is happening. Okay. There has been some change which leads to this kind of change in the microstructure. So, let us look at the phase analysis. This picture, obviously you can see here, this is the X-ray spectrum, where from the presence of this particular 3 peaks 111, 220 and 311, it is very evident or very clear that it is beta silicon carbide, right. And obviously there was a tungsten core. Tungsten is a very heavy element, so the signature of tungsten also appears in the XRD spectrum. All right. Now, let us do little bit more phase analysis in terms of doing Raman spectroscopy, okay, because SiC, beta SiC especially shows very good nice peaks for in Raman spectroscopy. So, Raman spectroscopy was carried out, and the outer layer has been shown here. So, this particular Raman spectroscopy is coming from the carbon coating at the outer layer, on the surface of the outer layer. Okay. So, what can be observed here, that there are two distinct peaks of carbon or graphite structure is D and G. D basically comes from the defect structure and G is the graphene structure. So, those peaks are clearly observed. Okay. Now, from this particular spectroscopic data, it is clear that the carbon which has been deposited, there are two things you can actually conclude from here. One is that this carbon which has been deposited is not perfectly crystalline, it is amorphous because of this peak which is quite broadened. Okay. Also, it is a very defective structure, it contains lot of defects in the graphene structure, and that is why you see very high intensity peak of the D band. Okay. Now, let us look at the core. So, this particular, you can see there are two spectra, okay, and these are coming from point A and B. So, if you look at this particular schematic, A, B is the inner points more close to the tungsten core. So, if you look at A and B, what you see here that there are two peaks, distinct peaks, and these peaks are basically denoted as transverse optic and longitudinal optics of SiC. That means, basically these two peaks are coming from the SiC material. Now, you can clearly see here again that these peaks are quite broadened and the intensity is quite low. That means, the grains are smaller or it could be amorphous as well. Okay. Most likely these grains are nanocrystalline, and that is why you see this kind of broadened peak and with very low intensity. And obviously, another important factor you can see here that this core, I mean this point A and B also contains carbon. Okay. This is interesting to note, and that is why this carbon peaks, okay, these are, you can deconvolute these peaks, and ultimately these are, this D and G bands have been clearly observed. As you move on from AB to CD in this schematic, in CD what you see is that these SiC peaks are now becoming more prominent. Okay. Along with that, also you can see that the carbon peaks are now, the intensity is getting quite low, and also you can see there is an appearance of a new peak of Si, and that things gets even more evident is that as you move to E and F point, you can see here that the SiC peaks have become quite prominent and the peaks are quite sharp. Okay. That means, now you are getting more perfect crystalline structure of SiC with large grains. Okay. And along with that, the carbon has completely gone out and you are seeing presence of Si peak now. Okay. So, let me move back to the microstructure once more. So, what you are seeing here that these grains are from the Raman spectroscopy. Now, basically it corroborates with the ACM result that the grains are quite smaller and not that perfect in terms of crystallinity, and then as you move outward you see that the SiC grains are becoming larger because the peaks were much more intensified. As you can see, these peaks are much more intensified. So, the grains have become much more larger and the crystals are also become more perfect. Okay. And what is happening here, as you move from the core to the surface, what you are seeing that in AB or CD there is presence of carbon, and then in E and F there is presence of silicon. So, what can you conclude from this particular data or particular set of information? That the partial pressure of hydrogen was being changed. Okay. Initially what you see, there is presence of carbon in the core. Okay. That means there was less hydrogen pressure, partial pressure, and as you increase the partial pressure of hydrogen, then you can see the carbon peaks goes out and you see peak of silicon coming. That means free silicon is coming into picture. So, that is what actually ultimately I wanted to discuss here, is that ultimately in case of E and F, SiC peaks are quite sharp and intense, and SiC crystallites are very perfect and larger. So, and that is all happening because of the effect of hydrogen partial pressure. So, students, one thing we have to remember very clearly is that in terms of synthesis of SiC fiber through CVD method, we should optimize the partial pressure of hydrogen so that we get stoichiometric SiC. So, now I will be discussing another technique by which SiC fiber could be synthesized. Okay. So, earlier I have talked about CVD, now I will talk about polymer pyrolysis. Now, do you guys remember about polymer pyrolysis? I discussed in couple of classes back that polymer pyrolysis means you will be having a long polymeric chain, and in that polymeric chain the elements will be present of which you want ultimately to make the compound. For example, we are talking about SiC here, that means this long polymeric chain will contain Si and C. Obviously, along with that it will be having other elements, and ultimately the aim would be to remove the other elements and to conjugate Si and C to get SiC, and this is done by pyrolysis of polymer at high temperature. So, in this particular example we are talking about synthesis of SiC fiber by polymer pyrolysis. That means obviously you need a long polymeric chain and which you are calling as precursor. So, in this case the precursor is basically looks like this. So, it is a organosilicon compound or organosilicon compound, and it looks like this: Si, CH3CH3, chlorine, chlorine, and it is called, that is why it is called dimethyl dichlorosilane, dimethyl dichlorosilane. And once you have this precursor, the first step is basically to get rid of this chlorine, and that is done by treating it with sodium. So, the chlorine goes out in the form of NaCl, and what is observed or what is found is this kind of structure CH3CH3 N, and this is called polydimethyl silane. So, polydimethyl silane is observed or obtained from here. The next step basically would be to find a chain of Si and C. So, this polydimethyl silane will be subjected to autoclave treatment, autoclave. So, take this material inside an autoclave and the temperature would be around 470 degrees Celsius. At that temperature you treat it for long time, 8 to 12 hours in argon atmosphere at high pressure, and then what will be observed or what will be obtained is this kind of structure. Okay. So, this is called let me write it here, polycarbosilane, polycarbosilane. Okay. So, once this polycarbosilane is obtained, then the aim, now see what is happening here, we have now got this particular atomic structure SiC, okay, in this polycarbosilane. So, the first step of after this polycarbosilane you get, the first step is to make it distilled. So, distillation is done, vacuum distillation is done, okay. And then after the vacuum distillation, what happens? The molecular weight increases to around 1500. Okay. Now, this polycarbosilane, the next step would be to spin it, melt spinning. Okay, to get the fiber out of the polycarbosilane. Okay. So let us just recapitulate once more that we started with a compound, basically organosilicon compound, which is dimethyl dichlorosilane, and that actually ultimately the chlorine gets removed and you get this kind of polydimethylsilane structure, and this polydimethylsilane in autoclave it forms this kind of polycarbosilane, and then distillation is done to improve the molecular weight, and the distillation, after distillation it is melt spun at around 350 degrees Celsius to get the fiber of polycarbosilane. We are yet to get the fiber of silicon carbide. Let me show you what happens next. So, as I was mentioning earlier, this is the particular structure of dichloromethylsilane, okay, and then ultimately after polymerization polydimethylsilane is obtained, and then it gets polycarbosilane, and then the vacuum distillation is done to improve the molecular weight. So, it still remains polycarbosilane, but then its molecular weight increases, okay, and this is the secondary precursor by which this ultimately the SiC fiber would be made. So, now this polycarbosilane fiber would be cured at around 190 degrees Celsius in air or in partial pressure of oxygen. Now, what is the role of oxygen here? If you remember about carbon fiber synthesis, there also the polymeric fiber was oxidized initially, and that we call stabilization. So, here also similar kind of stabilization is done. This curing is basically nothing but a stabilization process by which the polycarbosilane structure becomes rigid and stable at higher temperature, because now this polycarbosilane fiber will be subjected to higher temperature at around 1300 degrees Celsius in nitrogen atmosphere, and then the remaining other elements goes out and this SiC fiber is obtained. Okay. It could be amorphous or microcrystalline, and this structure is beta SiC, and this particular kind of SiC fiber is called nicalon. Okay. So, by polymer pyrolysis, in this particular slide we discussed that from polymer pyrolysis, by doing polymer pyrolysis, how you can get SiC fiber, and you can see here different forms of SiC starting from tau to matte to cloth. Okay. Tau means basically it is silicon carbide fiber being rolled in this bobbins, and then you have matte made by SiC fiber. It could be chopped, clothes could be made out of SiC fiber. So, there are different kind of forms. Okay. Now, let us look at the property of SiC fiber. So, what you are seeing here is that there are three different columns you see, and these are actually the different stoichiometric SiC fibers. Okay. As you can see here, all are nicalon fibers, but some is containing some amount of oxygen. Okay. And then these are actually high nicalon SiC fiber, and then this is completely stoichiometric SiC fiber. What is the difference in property? You can clearly see as you move towards more stoichiometric compound, the modulus increases to a higher value from 200 to 270 to ultimately 420 GPa, and also you can see here that the oxidation resistance and creep resistance also gets improved as you move towards more stoichiometric compound of SiC. An example has been shown here, a comparison between nicalon fiber, nicalon is also SiC fiber as I discussed just now, and then CVD SiC fiber. So, there are two different methods, one is CVD and the other one is polymer pyrolysis, and in these two it has been synthesized, these two different fibers. What can be observed clearly here, that the nicalon fiber shows higher creep strain. That means the creep resistance of CVD SiC fiber is higher. Okay. Because of this high temperature capability of these SiC fibers, these are mostly used at higher temperature applications such as, and it also have low neutron absorptions, and the neutron radiation stability of SiC fiber is also very good. That is why SiC based composites are quite attractive for use in advanced nuclear reactor systems. Okay. High temperature property, relatively low neutron absorption, and the neutron irradiation stability. For all these factors, SiC is mostly used in this kind of advanced applications such as nuclear reactors as such. Some more applications have been shown here. Heat exchanger for chemical industry, okay, fuel cladding in fusion reaction, reactor for chemical industry. Again, you can see all all high temperature applications where more strength and creep resistance are required, SiC fibers are used. So, ultimately what has been shown here, that the comparison of all the different fibers so far I have discussed. I have discussed about pan based carbon fibers, I have discussed about Kevlar, I have discussed about glass fiber, SiC fibers, Al2O3 and boron fiber. So, if we look at the different properties, what we can clearly see that boron fiber obviously is superior in terms of combination of high modulus and high strength. When it comes to combination of both these properties, modulus and strength, boron fiber is way better than the other fibers. Okay. On the other hand, E-glass or glass fiber does not show that much high modulus, but it shows fairly high modulus and fairly good tensile strength. Because of that, in most of the household commercial applications or regular commercial applications, glass fibers are used, where you do not need extremely high strength, but you need some amount of strength and modulus. That is where glass fiber is used. Another very important factor is quite evident from here, is that based on what kind of stoichiometry you have in SiC fiber, the modulus changes. For example, when you have very high stoichiometry compound which is made by CVD, you get modulus around 430 GPa, whereas in Nickelon it is quite low. Another important aspect here, you can see here, in case of carbon fiber only you can see clearly that thing, is that the modulus in the fiber axis and modular perpendicular to the axis is different. In the direction of the axis you see very high modulus, and when it is perpendicular then it is low, and that is happening because if you remember initially I mentioned that in the xy direction, because of sp2 hybridization, carbon sp2 hybridization, there is the strength and modulus is quite high. On the other hand, when you have the different graphene layers, in between that the bond is weak van der Waals bonding, and that is why the axis, perpendicular to fiber axis, the modulus is lower. In the next few minutes, I would like to talk about a different class of material which is whisker. Now, initially I mentioned about whiskers. Whiskers are basically single crystals, they do not have any grain boundary, and that is why they have extremely high strength. Basically, whiskers are defect free structures, and that leads to extremely high strength and high modulus for whiskers. And generally whiskers are having L by D ratio or aspect ratio in the range of 50 to 1000. So, in today's lecture I would like to discuss how SiC fiber or now SiC whisker could be synthesized. So, you can see in this particular flow diagram, synthesis of SiC whisker has been shown from rice hull. Okay. Rice hull or rice husk actually contains a very good amount of silicon oxide, SiO2. It also definitely contains carbon, and in a particular method this SiO2 and carbon could be combined, and ultimately SiC could be made, and this SiC is actually in the form of whisker. So, you can see here this particular reaction can take place, and then ultimately SiC could be obtained. So, what is done here basically? So, the rice hull that is grinded first, and then it is a coke is made basically by high pressure. The ground rice hull is transformed into coke form, and then it is taken inside a carbon tube reactor at around 1600 degrees Celsius. Okay. Once it is done here, when in this process basically this reaction takes place in the temperature range of 1500 to 1600 degrees Celsius, carbon and SiO2 reacts and SiC and 2CO forms, and this SiC, most of this SiC would be in the form of whisker. Obviously, it will be contain other fibers and non-stoichiometric compound as well, but it also contains SiC whisker, and then this ultimately the compound or the product which is obtained, that goes through cleaning and distillation process, and that leads to ultimately obtaining of SiC whiskers. So, by this process SiC whisker can be made. However, the purity of the whole product is not very high, or in other way the percentage of SiC whisker in the whole product would be not that high. So, we need to go for a better technique, and that technique is this VLS process or vapor liquid solid process. Okay. From the name you can clearly see that there is presence of vapor phase, liquid phase and solid phase. Now, vapor phase is basically the precursor material. Okay. So, let me show you what happens. So, there will be a substrate, and on the substrate there will be this this steel balls, irregular shaped, will be sprinkled like this, and then this chamber would be heated at a temperature of around 1400 degrees Celsius, right. So, it is a closed chamber, there is a substrate, generally it is a silicon wafer, and on the substrate these steel balls or steel particles are basically small particles in the range of 15 micrometer only, are sprinkled, and then the whole chamber is raised at a high temperature around 1400 degrees Celsius. At the same time there will be vapor feed. So, here CH4 and hydrogen gas will be incorporated. At the same time SiO will be incorporated in the form of gas also, SiO. How do you get SiO? So, by the reaction of SiO2 and carbon, it gives SiO plus CO, okay, and the temperature is requirement is around 1500 degrees Celsius. So, anyway, from this reaction this SiO is taken and SiO is fed in the chamber. Now, because of high temperature, what happens, these steel balls will melt, okay, and in the molten steel ball these gases will diffuse. Actually, what will diffuse? Carbon and silicon will diffuse into these molten steel balls, and then what happens, ultimately the concentration of carbon and silicon keeps on increasing, and at a certain stage these molten steel balls will be highly saturated or supersaturated with carbon and silicon atom. The moment it happens, then so now you have a steel ball which is supersaturated with carbon and silicon, and then because of the supersaturation carbon and silicon reacts and forms SiC, and it gets deposited like this. So, in the next stage you will be seeing a whisker is growing like this, and then on top of that there is a steel ball. Okay. Let me show the schematic once more here. You can clearly see here. So, as I was mentioning earlier that you have this substrate, on the substrate these solid catalyst balls are actually, so this is solid, so that is the vapor feed. You have a solid catalyst, and ultimately the liquid phase is basically this molten steel balls, and then by supersaturation of silicon and carbon, ultimately the growth of single crystals of SiC takes place. And as you can see here, the growth of Whiskers rate in 10 hours, it is quite small, quite less, 10 to 20 millimeter only, but ultimately you get a very nice and very kind of monocrystalline, single crystalline SiC Whiskers. Okay. And you can remember here clearly the strength here is 8.4 GPa and modulus is 581 GPa. If you compare that with the earlier SiC, which is around 430, okay, and the strength is around in the range of, as you can see here, 3.5. So, in both terms the strength and modulus both are quite high in case of SiC Whiskers, 8.4 GPa and 580 Young's modulus. Okay. So, this is how it looks like, as you can see here. Okay. This is how it looks like, the Whisker growth. So, ultimately I would like to conclude saying that we talked about SiC carbide fiber synthesis and also SiC Whisker fiber synthesis, and we discussed that stoichiometry is extremely important in terms of fibers, SiC fibers. If you have better stoichiometry, that leads to better modulus and strength, and we talked about Whisker also, synthesis of Whisker by a special process called VLS method, and we observed that the strength and modulus of Whiskers are quite higher than the fibers. So, with that I would like to conclude, and in the next class I will discuss about metal matrix composites, their basic concepts, and we will also discuss about the different processing routes of metal matrix composite synthesis. With this I conclude here today, and I will be welcoming you all again in the next class. Thank you all.